This is Sukriti Joshi. Our today's topic for this particular video session is the nuclear reactors. We all know that nuclear reactions will give us tremendous amount of energy, right? So it is all about the imbalance of protons and neutrons. We all know that atomic nucleus contains protons as well as neutrons. Now, when the protons and neutrons and the number of protons and neutrons becomes unstable at that particular time, they will produce nuclear or they will produce radioactive radiations plus tremendous amount of energy. Now, this tremendous amount of energy can be utilized to fulfill our energy requirements. We can actually use them to fulfill our energy requirements. As we are lacking different sources, that is, we are lacking already in crude oil, in different petroleum products, so it is a very good option to use it for our energy requirements. Okay. Now, let's take a look on how the nuclear reactor works and what is the meaning of actually the nuclear reactor here. So we will have here two different types of nuclear reactions. One which is known as nuclear fission, while another one is known as nuclear fusion. So nuclear fission will give us the energy which we can use, while nuclear fusion will not give us the energy which we can use in any other particular way or in useful way. So that will give us an idea that which kind of reaction, which kind of nuclear reaction that we can utilize here, right? So as you can see in the image, we will have a reaction which occurs in particular manner. Okay, so as you can see here, it will contain three different compartments. First compartment is a concrete shield compartment or concrete compartment. Second one is coolant compartment. Third one is turbine generator compartment. Okay, so it can be easily observable here that first compartment contains the first one, which is in concrete shield. You will have a steel shield. Okay, so concrete shield in which we have a steel shield. That steel shield will have uranium-235 fuel rods and movable boron-10 control rods, right? So they both are placed in coolant water moderator, right? Coolant water and moderator. So it's dipped uranium-235 fuel rods and movable boron-10 control rods in the moderator, in the coolant. Okay, so the reaction occurs in this particular steel shield compartment, and that steel shield compartment is again protected by a concrete shield compartment. Okay, because radioactivity can penetrate any material, so we need to make sure that it should have a particular thickness, it should have a particular material, a particular thickness of material has to be there so that it can't travel or it can't leak in an environment, otherwise it will cause great loss. Okay, so here what will be there, that particular coolants are generally, again as you can see it in the image, that coolant is continuously rotated or movable. So first what you will do here is basically the coolant, okay fine, the coolant that is added in the steel shield. So at that time what will happen, the reaction is going on, a huge amount of energy will be released. So the temperature of coolant when it enters the steel shield, at that time it's 280 degrees Celsius. Now the reaction occurs in the steel shield, right? So that nuclear fission of uranium-235 occurs and it will produce energy. So it will raise the temperature of the water. So the temperature of the coolant water will be raised from 280 degrees to 320 degrees. Okay, so the raise in temperature, that 40 degrees Celsius raise in temperature occurs, and that coolant, the higher temperature coolant water is moved to the coolant compartment. So that in that compartment we have water from the sea. So that particular higher temperature water will raise the temperature of the sea water also. Okay, and that will create steam. So that steam will be further moved to the turbine generator that rotates the blades of the turbine, and the energy will be produced. So what we will do here, we will convert here our chemical energy, that is our the energy which is produced during the nuclear reaction, that is known as nuclear energy. So that nuclear energy gets converted into steam, and that steam gets converted through the turbine in the way that particular energy can be used further. Okay, so in that manner, this is basically the conversion of energy occurs and the nuclear reactor works, right? So it has been possible to control the fission of uranium-235 so that the energy released is slowly, or that releases at slowly usable rate. Controlled fission is carried out in a specially designed plant called a nuclear power reactor, or simply a nuclear reactor. The chief component of a nuclear reactor are: number 1, uranium-235 fuel rods, which constitute the fuel core. The fission of uranium-235 produces heat energy and neutrons that start the chain reaction. Number 2 is moderator, which slows down or moderates the neutrons which are produced during nuclear fission. The most commonly used moderator is ordinary water. Graphite rods are sometimes used. So here neutrons slows down by losing the energy due to collisions with the atomic molecules of the moderator. Our third one is the control rods. So control rods which control the rate of fission of uranium-235, and these are made up of boron-10 or cadmium that absorbs some of the slowed neutrons. Okay. Number 4, the fourth part of this one is coolant, which cools the fuel core by removing heat produced by fission, and the water used in the reactor serves both as moderator and coolant. So here we will use heavy water is even more efficient. So D2O can also be used here. And the last but not the least, the fifth part is concrete shield, which protects the operating personnel and environments from destruction in case of leakage of radiation. Now the next one here is light water nuclear power plant. So most commercial power plants today, which are used today, are light water reactors, and in this type of reactor, uranium-235 fuel rods are submerged in water. Here, water acts as coolant and moderator, and the control rods of boron-10 are inserted or removed automatically from spaces in between the fuel rods. Now, the heat which is emitted by the fission of uranium-235 in the fuel core is absorbed by the coolant. The heated coolant, that is the water at 300 degrees Celsius, then goes to the exchanger. Right? That compartment is exchanger compartment. So here the coolant transfers the heat to seawater, which is then converted into steam. Now this steam then turns the turbines, generating the electricity. Okay, so in that manner we can produce energy. It will give us energy. A reactor once started, it can be continued to function and supply the power for generations, because these are basically chain reactions, self-generated reactions. About 15% of consumable electricity in USA today is provided by light water reactors. And India's first nuclear power plant went into operation in 1960 at Tarapur, near Mumbai. Another plant has been set up at Narora in Uttar Pradesh. While such nuclear power plants will be a boon for our country, they could possess us, or they could pose a serious danger to environments also. Say for an example, in May 1986, the leakage of radioactive material from the Chernobyl nuclear power plant in USSR in Russia played a havoc with life and property around. And that particular leakage of radiation goes to the US. So it can actually cover a huge distances. Disposal of reactor waste possesses another hazard. The products of fission, for an example Ba139 and K92, they cannot be destroyed. They are radioactive in nature, and it is packed generally in concrete barrels which are buried deep in the earth or dumped in the sea. But the fear is that any leakage and corrosion of the storage vessels may eventually contaminate the water supplies, and it eventually contaminates whole environment. So it will cause a huge accident if any kind of leakage occurs there. Next one is breeder reactor. So we have seen that uranium-235 is used as a reactor and fuel for producing electricity. But our limited supplies of uranium-235 are predicted to last only for another 50 years. It has been seen that we have our fuel for a very small period of time. So that particular part creates a huge problem. We have to find a solution for fuel shortages, and this plays a very important role. Breeder reactor can actually use a tremendous amount of energy. However, non-fissionable uranium-238 is about 100 times more plentiful in nature. Uranium-235 is available in very small amount, but uranium-238 is available in a very huge amount. So this is used as a source of energy in the so-called breeder reactors, which can supply energy to the world for 5,000 years or more. Here, the uranium-235 core is covered with a layer or blanket of uranium-238. The neutrons which are released by the core are absorbed by the blanket of uranium-238. This is then converted to fissionable plutonium-239. And it undergoes a chain reaction producing more neutrons and more energy. The above reaction sequence produces 3 neutrons and consumes only 2. So what happens here? As you can see, we will use here a very small amount of uranium-235, but a very huge amount of uranium-238. So in this manner, we have a very large amount or plenty amount of uranium-238. So that plays an important role, that by using smaller quantities of radioactive material, we can carry on, or we can get a huge amount of energy. Okay, so this is the best example of how we can utilize our knowledge in this particular manner. Now, as you can see here, the reaction which will be carried out is 92 uranium-238 will be bombarded with 0 or bombarded with neutron 0 and 1. So it will produce 94 plutonium-239 and produces 2 electrons. Okay, -1 E0, that is the symbol of electron here. Now that 94 plutonium-239 is again bombarded with the neutron. So that neutron, which is shown by 0 and 1, will produce 38 Sr90 plus 56 Ba147 plus 3 neutron particles. And in this manner, it will continue to give us energy. Now the above reaction sequence produces 3 neutrons and consumes only 2. And the excess neutron goes to convert more uranium to plutonium-239. Thus the reactor produces or breeds its own fuel. And hence, its named several breeder reactors are now functioning in Europe. However, there is opposition to these reactors because the plutonium so obtained can be used in the red H bomb. So it's very dangerous because it can be used to produce H bomb, or not produce H bomb, but can be used in H bomb. So hydrogen bomb is a very huge danger for our world. This is all for this session. Thank you so much, everyone.